Good morning. Let's start the morning session today. The first speaker is Professor Eric Urban from Columbia University. He'll talk about Euler system and congruences.
Okay, thank you very much for the introduction and for the invitation. So a few years ago, I gave a different construction of Euler system of cyclotomic units using Eisenstein congruence for GL2. And so today I wanted to explain how we can apply the same principle to construct an Euler system for the orthogonal representation attached to Siegel modular forms and prove a direction towards the main conjecture for this. So let me introduce notations and hypothesis. So pi is a cuspidal notation of sp2n over q. I will often consider actually just a representation of GSP2n, but only the restriction to sp2n actually matters. So I assume that in such that pi infinity is in the automorphic discrete series. And I will assume that pi p is unramified and ordinary. So thanks to the work of many people that I'm not going to list here, we know that we have a Galois representation, rho pi, from the absolute Galois group of Q to SO to n plus 1 of O, where O is a finite extension of ZP. And so by ordinarity of pi p, we know that rho pi restricted to the decomposition subgroup at P is upper triangular. So actually, I'm going to just describe the restriction to the inertia, which is going to be on the diagonal, you are going to have the cyclotomic character to several powers, K1, K2, 1, and then the inverse. Minus K1. And so here, K is going to be K1, Kn. And so K1, K2, Kn 0 minus Kn minus K1 are the state weights. And so from this description, so we know that, so if we call, let's say T rho, the O pre-lattice over which GQ acts by this representation, so we see that these vectors gives a filtration that I'm going to call F plus, and this vector gives a filtration that I give for F naught. So this allows to define a Selmer condition. Greenberg. And I'm going to call S L to infinity rho, the corresponding Selmer group. And so which was defined by Greenberg in this generality. And we know also that we have a periodical function which has been originally constructed in this setting by, I think, Böcherer and Schmidt, but which has been extended by Zheng Liu for actually families of such representation, and that interpolates the critical values of L by actually, I'm going to switch. I'm going to twist by some character alpha here, finite order character. So here alpha is a finite order character. Well, the original character, let's say. Psi L. And so psi is p-power conductor character. And L is a critical value. And I think it should be between Kn plus 1, 0. Okay? So I'm going to make some assumption. So, excuse me? Well, I'm not saying that I have all the critical strip here. I'm just going to consider this one. Yes. Oh, sorry, K. No, it's because actually L is going to become Kn plus 1 later. That's why. Okay, so some assumptions. So the residual representation rho bar, so I'm going to call it rho now, is going to be absolutely reducible. There is some conditions of big image for rho bar that I'm not going to state, but the most important assumption is that the splitting field of K rho bar should not contain Q of mu p. And I believe that this is satisfied very often, but I haven't bothered to check all the conditions. All right. So this condition is actually implies some global genericity condition for later use. And it's possible that it could be avoided, but for now, I don't know how to do that. Okay. So the theorem, main theorem. So I should say that I'm going to put a star because this is still work in progress, and some of the ingredients are still being written by some people, but once they are being written, then it should be complete. Is that as the dual the Selmer group infinity of tensor alpha. Quatergin dual is a distortion over the Iwasawa algebra S. And its characteristic power series excuse me? Q infinity. Yeah, sorry, Q infinity is atomic extension. So divides the predicate function. So, going to give an M, LP. Okay, so I have to S here, I just relax the condition at primes S, where S is a set of ramification of pi and alpha. Okay. So probably Greenberg proved that this implies, implies the full conjecture even at S from this. Excuse me? Yes. I didn't understand what you're saying. Oh. Oh. Yeah, this is in lambda, of course. Yeah, you know the translation, right? Okay, so so the method is a Euler system. Oh, excuse me. I should say something. Yes, thank you. Actually, so divides in lambda 1 over p. Okay. So if I want to have the result for lambda, then I have to assume a bigger image assumption here. This is something that is needed to apply Rubin's method. Okay. So, method. Okay, so therefore the main point to prove this theorem is to construct another system. So construction. So I'm going to explain the first in the case where n is equal to 1. What is the idea to construct this? So constructing another system is to construct families of homology classes that satisfy certain normalations and which are integral. And that allows to, using the Colli-Vagin derivative technique, to construct ramified classes of torsions and use global reciprocity law to bound the Selmer group. So for n equals 1, so basically this is looking at the adjoint representation, excuse me, not n equals 1, n equals 0. So this is just looking at one character, because if you, going to give it one character, the dimension is 1. So in that case, we want to look at Eisenstein series for GSP2, which is GL2. So if you fix a character chi, Dirichlet character chi, and a weight L, then you can consider an Eisenstein series of weight L plus 1. Oh, excuse me, I forgot to give an assumption here. So the assumption is alpha minus 1, alpha of minus 1 equal to minus 1 to the n plus 1. Just parity condition. This one? Yeah, so basically, I don't want that the image of rho bar as an abelian quotient, which is going to correspond to the Galois group of Q of mu p. So you can look at this Eisenstein series of weight chi. So let's say assume here chi is ramified at p. And then from this Eisenstein series, you can form two Eisenstein series, which is what we call the ordinary Eisenstein series. And you can form also the critical Eisenstein series. Okay, and so here's the eigenvalue of the UP operator is going to be 1. And here's the eigenvalue of the UP operator is going to be chi of PL, chi of P to the L. And now if we use the theory of p-adic families of modular form, so the family of modular form containing this Eisenstein series is what we call a Hida family, actually, which was invented before Hida by Serre, is a family of Eisenstein series. And this one, because it has a slope, positive slope, you get a family which called the Coleman family, which gives a family which is generically cuspidal, except at this point. But here we have a family of Eisenstein series. So if you look at what's going on the level of Galois representation, so you get here a family of reducible Galois representation. And here you get a family of generically reducible Galois representation. So if you use Ribet's method in these two cases, so what you get here, you can construct when P divides the constant term of this Eisenstein series, you can construct non-trivial extension of this form, chi epsilon L. But this is going to be torsion classes here. And here, torsion classes, and by the ordinary condition, you'll know that this torsion class is actually unramified at P. And here you do the other way around. And you get actually non-torsion classes, which we don't know what's going on at P, but we know it's going to be actually ramified at P in most cases. The fact that it is ramified at P or not is going to depend if the corresponding point in the eigen curve is actually the étale over weight space. But if we, and it's going to be related to a kind of Leopold conjecture saying that the periodical function evaluated at L is actually non-zero. And this is something that does not happen generically when the weight varies. So it's not going to be a problem. So this, you see, gives a class in H1Q QP of L, reset by chi, which is the same as a class of Q of mu n if n is a conductor of chi or level of chi, let's say, QP of L. So, for instance, if the weight is 2, so here what you get is just the projection of a cyclotomic units on the chi part. And therefore, the original idea is to patch all those classes for various character chi of level n to actually build the cyclotomic units at level n. So of course, there is a big difficulty, which is to clear the denominator in a compatible way so that you have all the norm relation. So basically, the point is to make this construction of Coleman here in a canonical way so that you can build the Euler system. So this is the main idea that I want now to carry out for GSP 2n plus 2. Okay. So now if you take psi, a Dirichlet character on L, and if you make good choice of sections, you can construct Eisenstein series for pi and psi of a certain weight. K bar. So in that case, K bar is going to be K1, Kn, L. And so this Eisenstein series is attached to a Galois representation in SO2n plus 3. So this is going to be an Eisenstein series of on G S P 2n plus 3 G, group G. And you see that H, it has a parabolic subgroup, a Lingen parabolic. Such that the Levy is going to be GSP 2n. Yeah. So we are going to put pi on GSP 2n, and we are going to put psi of L on this GM part. And and then one has to make some good sections for the corresponding parabolic induction to construct this Eisenstein series. So the fact that here we get something ordinary or critical actually depends on the choice of the section at P. And here something similar happened. So we have to make good section at P to get an ordinary Eisenstein series and or a kind of critical Eisenstein series. So anyway, so the Galois rotation in SO2n plus 3, so rho E, in that case, is going to be given by the rho pi, I defined before, and then you are going to have here psi epsilon L, and here psi inverse epsilon minus L. And so here again, we want to apply Ribet's method. So we are going to get something here, something there. And I'm looking at this in characteristic 0 now because this is what I want to do. I want to construct, I want to construct characteristic 0 classes. Okay. So the fact that we can get this in this order, it's because the representation rho and its deformation in a kind of Coleman family, in that case, are going to be generically reducible and orthogonal. And this orthogonal condition can assure that actually we get this order. Okay? And so if you write this way, this element here is going to give you a class in H1 Q rho tensor psi twisted by L, which is the same as H1 Q of mu n rho of L. Yeah, so tensor maybe let's be 1 over P. Okay, and so of course we want to do the same thing. Actually, we want to make this construction actually integral and canonical. Okay. And this is by doing so that when we restrict the class at P, we are going to see the p-adical function. Well, yeah, this is a kind of a generalization of Ribet's lemma. Yes. So generalization. Yes, but what I was saying is that so here and also in that case, we apply Coleman theory. We get a family of modular forms which are generically cuspidal. And therefore, that means that you have many congruences modulo high powers of P for which you can apply Ribet's lemma. do you get the canonical element? How do you choose the canonical element? Oh, this is the object of the rest of the talk. Yeah. Okay. So, so I want to give a little remark about Ribet's lemma. So what is, I'm just going to explain that for GL2 for simplicity. But so if you look at the matrix of the Galois rotation, which is cuspidal, which is attached to, which is congruent to the Eisenstein series, so you can write your matrix like this. And so what Ribet does to construct this lattice, because this representation is irreducible, you know that it's not going to be upper triangular. So the product of those two elements are going to be non-zero. And so choosing a lattice is actually multiplying by something like this. May take conjugate by something like this. You see? And so, so when you do this, you multiply this guy by p to the 2n, and you divide this guy by p minus 2n. So, yeah, maybe you want to do this rather. And so that means that when you do this, you can decrease the valuation of the right shoulder so that it becomes non-zero mod p. And then when you reduce modulo, what you get is something which is non-zero mod p, and then you have your class. But if you think of this, when you do this, what you do is that you just multiply this guy by a power of p, and you divide this by the same power of p. So therefore, b sigma c tau for two elements of Galois is actually unchanged. Okay, so instead of doing this kind of silly operation, it's better just to look at this value, which is canonical, and that belongs actually to the kernel of the map that gives, from the equal algebra that gives a map to, so this belongs to P, which is the kernel of, let's say, the equal algebra that goes to O, and where this is the Eisenstein eigensystem for T. Okay. So the advantage of this is that you get something integral immediately, and that helps you to build everything. So you can just make a good choice for tau, and then you just look at look at this quantity modulo the kernel of P. Sorry, modulo the kernel of this, which means actually you look at, so this is, the fact of looking at this is actually was invented by Wiles when he defined the notion of pseudo-representation. So X sigma tau, he call it. And if you normalize it with a character of, I mean, in that case, chi epsilon L, you get something prime, let's say, it's going Y. And this mod P square gives you a cocycle, but it's not a cocycle taking integral value. Really, it takes value in P mod P squared. Okay, so so the structure of this module is much more difficult to understand, but we'll see how we can deal with this problem. So one of the main ingredients to solve this problem is to use periodic long-length correspondence for GL2QP. This is the only one that is available right now, but it is sufficient for our purpose. And so what I'm going to do is that I'm going to introduce a Q parabolic of G of QP such that the levy is MQ is going to be GM e power n cos GL2. Okay. And I'm going to consider peak pi representation of G over Q. So G GSP2 n plus 2 here. And which are Q ordinary. And so instead of explaining what exactly Q is, I'm going to tell you what it does on the Galois representation. So that means that if you look at the standard Galois representation, goes from GQ to SO now 2n plus 3 of some Q bar. Then in that case, rho pi restricted to the decomposition subgroup is going to be something like theta 1, theta n. Then you are going to have sigma, and then theta n inverse, theta 1 inverse. So here, the theta i's are characters. And psi is going to be a self-dual, actually orthogonal. Galois representation of the decomposition subgroup at P. And actually, you can see that psi is actually the adjoint representation of some representation theta, which is now theta is going to be dimension 2. Okay. So this is the shape of this Galois representation. So if we place ourselves in the case where n is equal to n is equal to 0, so actually psi is just trivial. But so if we can put ourselves in a no, sorry, when psi is equal to 0, I mean, sorry, well, yeah, n equals 0, just psi is trivial. And actually, instead of working in PGL2, just write directly in GL2. And then what we have is just theta. But so here, we cannot do that. We cannot say SO2 n plus 1 as PG of something in general. Yes, but actually the central character is not playing any role here. So, because when you look at if you have a central character, sorry, for the Galois optation, if you have a central character, because the extension are going to, if you have a central character, that means that you twist representation by something, and this something does not play any role in the construction of the cocycle. So it doesn't matter. You can choose any lift of your representation of SP2n plus 3 to a representation of GSP2n plus 3. You just could make a choice. It doesn't matter. Okay. So the method to treat this case here, the way that one can construct the classes in a canonical way, one had to leave the realm of the eigencurve, because the eigencurve, except for the ordinary component, does not have good integral properties. So the method, therefore, was to use actually the whole periodic equialgebra without putting any condition at P on this equialgebra. And that meant looking at the periodic equialgebra without putting any equioperators at P. So that looks strange a priori, but that's the only way that we can look at all the possible Galois representation locally at P. So let's consider EQ, the pure ordinary Galois, equialgebra. So acting on, so it's something I'm going to call H tilde compact Q, which is the inductive limit over KQN of H D of S. So this is going to be the Shimura variety attached to G. So I'm going to fix an open compact subgroup away from P. And here I'm going to get at P, KQN, and with coefficient in QP mod C. Okay. So, and I take this the Q ordinary. So again, I'm not going to explain what that means. That just means that certain equioperators act invertibly. Yes, I'm going to explain what it is. Yes. So KQN is the set of gamma in G of ZP such that gamma mod Pn belongs to UQ of Z mod Pn, where UQ is a unipotent radical of Q. Okay. So the advantage of this is that, well, all the automorphic forms that are going to show up in this are going to be Q ordinary in that sense. And moreover, it inherits of an action of MQ of QP, and particular, it's going to be GL2 of QP plus QP to the n. Okay, and so it has a compact compact subgroup, which is going to be so GL2 ZP maximal compact ZP cross to the power n. Okay. So, me? Yeah, Krigopy cross, thank you. Okay. So, so a priori it's kind of clear you have an action of those two groups. It might not clear why you have an action of this, but that comes from the fact that you have the echo operators at P that defines the Q-ordinarity that contract sufficiently the unipotent to even let the denominator here act. So, yes, exactly, because this ordinary, I mean, this echo operator at P are actually supported on this part, not here. Yeah, I don't have time to explain in details. I'm already out of time. So to make things integral, so of course this echo algebra is so I didn't say which operator you put in, but you put in all spherical operators. And you consider all the diamond operators attached to this ZP cross to the n. Okay. And so it gives you already an action of lambda q, which is going to be O double bracket T1 Tn on this so on this module and on this echo algebra. So this echo algebra is a lambda q algebra. Okay. So for one side, so by the assumptions I made, oh yes, excuse me, I forgot to say that I'm going to localize at some maximal ideal, which is attached. So this maximal ideal is going to be Eisenstein of Klingen type. The Klingen type Eisenstein series that I'm considering. I don't know whether I wrote them, but attached to the Eisenstein series. No, I erased it. It was the one that was written here. So the one that was giving Galois rotation of the form rho pi psi epsilon L, psi epsilon L inverse. Okay. So that gives you certain maximal ideals, and I'm going to consider when you psi vary psi, sorry, alpha. So when you vary alpha among the alpha which are congruent to each other, and when you vary pi among a representation rho pi which are congruent to each other, then you get a maximal ideal. And this is that kind of maximal ideal I'm considering here. So under the condition that I've made, this genericity condition I have made, then using a recent result of Yang and Zhu, we can show that actually everything that shows up here comes from characteristic 0. And using that, we can see that we have Galois representations. And in particular, we have, if we want now to put things, to make things integral, we have a pseudo representation of dimension 2n plus 3. Okay. Moreover, so let's call it psi m that goes from GQ to this EM. Maybe I should put Q to remember QM. Maybe I should put M here also. So we have this Galois representation, and now we have also a character I'm going to call lambda Eisenstein. So that takes value to now to the component of the equal algebra, but now for the group GSP2n, which is the one attached to pi. Remember, pi is on GSP2n, and tensor a group ring, delta n, that I'm going, which is also localized. This is a local component of this again. Here, delta n is E mod n cross, because actually the n shows up in here. I forgot to mention it, but you have some label here. So this group may have several components, so you have to deal with each component. I mean, actually, there is only one component I'm going to be interested is the component where the characters are actually going to be congruent modulo p. So, because this is only those ones that are useful for the Euler system argument. Oh, okay. So, can I get 5–10 minutes? 5 more. Okay, so the point is that, so you have a kernel, it's lambda E, and modulo this kernel, so what you get is you get all the something like this, trace of rho T and pi. And here you have also the universal deformation. And here the deformation. Yeah, so you have to put P infinity here. I forgot to say. And NP information. And by this way, you can define a cocycle that takes value in H1Q of rho T M tensor alpha, tensor this P modulo P squared. Okay. Exactly as I explained for the GL2 case. So now the point is that you have R, which is going to be the universal pseudo deformation ring. Of GQP, which deform forming so zeta bar, zeta mod P. Remember, C, sorry. And remember, because rho pi is ordinary, when you look at this modulo P, you just have a sum of characters. Okay, so therefore this psi, which was a priori irreducible, which is irreducible, when you look at introduction mode P, it becomes reducible, and it's just going to be congruent to zeta plus 1 plus theta inverse. So this is, and because psi is just, oh no, that's chi. So alpha inverse, restricted to GQP, of course. And so therefore, this alpha is actually the alpha restricted to GQP is 1 plus alpha is going to congruent to this theta here. So the point here is that this ring lock, and I'm going to also with fixed determinant, is going to be to have an element that I call X red, which is generating the reducibility local locus. So this is, I mean, it's not always exactly the case. It's the case only when this ring is formally smooth. When it is not formally smooth, which is in the non-generic case, then we have to treat that separately. But essentially, everything can be done with this guy. And now, so the main point is that TQ modulo this X red Q is related to the ordinary equialgebra for G. Not only Q ordinary, but B ordinary. And so what we do is that we look at the exact sequence, P modulo P squared, P red modulo P squared red. And here, well, this is, well, X modulo X squared, but this is free. So So therefore, what we get is R red, which is just R log divided by X red. Okay. And so a priori, it's not clear this is injective, but one can prove this is injective because this is free, and to prove the injectivity, it is sufficient to inverse P. And when we inverse P, then this becomes simple because of the existence of this critical family. And this is a multiplication here. So you have to look at this exact sequence of this controlling all the deformation, here controlling all the ordinary deformation because of this relationship here. I have to say that this relationship here is obtained using the local Langlands correspondence. I don't have time to explain. But this looks like a congruence module for ordinary Eisenstein congruence. So therefore, this guy must be annihilated by the periodical function. On the other hand, one can see that, so if I take the notations for GL2, the equivalent that corresponds to this X sigma tau in this context, this guy, when sigma and tau run in the Galois group of GQP, generate the reducibility ideal. So therefore, you can choose sigma and tau such that this guy is X red. And because this is just multiplication by X red, the co-cycles that you get that is taking values in P mod P squared tensors the representation, when you project on the gross zero after restriction to the decomposition subgroup, then it becomes already integral here. And actually it generates here because this guy is because you can choose a sigma tau naught such that this is X red. So therefore now if the co-cycle you have gotten here, you multiply it by this periodical function, then because the periodical function is going to annihilate this module, then it takes values here. Therefore, it is integral and canonical, as long as this periodical function is well chosen. And moreover, when you restrict to the decomposition subgroup, then it's like multiplying by this guy. So therefore, you get exactly the periodical function. Okay. So this is how you make the construction integral, and this is how you get the reciprocity law. So now, what I said here, we don't have an isomorphism. We have a map, which is surjective and which is actually, one can prove it is, the kernel is going to be nilpotent, but this is not enough. So instead of using this, one has to use a similar exact sequence, but instead of by replacing Eke algebra by a Eke module. And the Eke modules that we consider is the one I explained here. Okay. And there is another ingredient because this is cohomology. So to study the congruence module for cohomology, you have to lose classes in cohomology. And determine that classes in homology are integral is very difficult. But here what we do, what I do is I connect this cohomology to lambda-adic modular form using a generalization of Ota's map, which has been figured out by using some work of Gulota and Chow. Okay, so I'm going to stop here. Sorry for going over 5 minutes.
Yep. Thank you very much. Other questions, comment?
Oh, I mean, so this is in the non-generic. So in the generic case, this is very simple. So this is reducibility ideal for GL2 because everything is actually the adjoint of something with GL2. And so when you look at the deformation, the local deformation for GL2, then you can see that you can see that actually in the generic case, all pseudo representations are actually congruent to something like omega chi 1 star. You have exactly one unique extension like that because chi is not omega or omega inverse or non-trivial. And therefore, in that case, you see that the deformation ring for this is the same as the pseudo deformation ring. And because of this chi is not equal to omega or omega inverse, then the H2 of the adjoint representation is trivial. So this is formally smooth. So therefore, you know that the deformation ring is of this form. And now, when you look at the reducible locus, you just deform one character because the determinant is fixed. And therefore, you get something like O double bracket X prime Y prime, okay? So therefore, you see that that means that this surjective map must be generated by a regular element. Okay? Those two are just regular rings. Okay. Yes. So where it is used to show this kind of relationship. Basically, because when you look at this, you are seeing that locally, your Galois representations are reducible. And for GL2, saying that the Galois representation is reducible means that the automorphic form is ordinary or anti-ordinary. And so this is how you connect this to ordinary equialgebra. No, periodic Langlands, because mod P is not enough. I need really to have the whole periodic Langlands. So something I didn't have time to explain is that so when you look at psi m restricted to GQP, then you have a sum of characters, and then here you have this what we call it psi. And this psi deform, okay? So therefore that means that you can you have a map from R log to TQ, okay? And so therefore it's why you have this X thread here, and now this this R log is what is it? I said this is now this R log you can identify as the uniform deformation of 1 plus theta. No, well, yeah, I call it theta over there. And so now you can look at a block in the category of locally admissible representation of GL2QP. that correspond to the induced from the parabolic to GL2QP of theta tensor 1 and sorry, omega. Yeah, I don't remember omega. Yeah, that. And so if you take the injective envelope of each of these blocks, and you take the endomorphism of this, then in the non-generic case, sorry, in the generic case, the local Lagrange correspondence gives an isomorphism here. This is Pascuna's word. And so this is how you make the connection.
Any other questions?
So in this case, the periodical function is obtained as image of your Euler construct.
Yes, yes.
So
yes, because it comes from the fact that so when I construct the Euler system, I have to choose something here. So but so in the case, I'm not considering this exact sequence. I consider an exact sequence for modules, and I can write it down. But what happens is that I have to choose some sections from the parabolic induction, and a section that has been that plays a role in the construction of the families of Eisenstein series, in that case, which has been done by Zheng Liu. And the periodical function that shows up at the end is going to the one that comes in the constant term of this Eisenstein series. Well, the reciprocity law comes from the fact that when I restrict to the decomposition subgroup, as I said, everything takes value in here already, because this guy is going to actually, sorry, it's not X red, it's going to be lambda G answer X red in that case. For GL2, you have just X red, but in that case, you have this lambda G. So actually, so if you do that, you get actually an Euler system directly for the whole family. But then you restrict it to any point of your family, and you get the one that you use for the main conjecture. No, what I do is, so I have so, and this is using the really the local Lagrange correspondence. This is to show that several things that are needed to show is that this x tilde q m that I've considered, so it has an action of, you have an action of R log tensor lambda q, and so something that needs to be shown is that when you divide by X red, then you get that this is H tilde M now, B ordinary, for one maximal ideal of the ordinary equialgebra, and plus H tilde B M2 for the other, because you can have two maximal ideal in the ordinary EQ algebra according to the orders you put to the characters. Okay, so you see for GL2, when you restrict to the decomposition subgroup, if this is reducible, you get something like this, and then you have a star here or here. Okay, so if you get the star here, then you get the maximal ideal M here. If you get the star here, you get the maximal ideal M2 here. So it's why you have two components. So this isn't the case where the two characters are distinct modulo P. If they are not distinct modulo P, then in that case, there is only one maximal ideal. And in that case, it's known also that the reducibility ideal is generated by one element. But you cannot a priori, it's not easy to construct the corresponding Galois representation, but you can. You have to extend scalar. It's not defined over R log, but something a little bit bigger, which is not very complicated, but I mean, it's something which is done in Pascona's work. So in the other, there are two non-generic cases which are difficult. This one is the simplest. The other one is when the ratio is omega or omega inverse, and then it's like almost 1/2 of the paper. Yeah. So in that case, R red. So in this non-generic case, actually, the reducibility ideal has two elements, and so when you compute I mod I squared, then you get, don't remember exactly, but I think you get something like R red plus something like O or something like that, I don't remember. But everything works down if you project everything over R red. But yeah, it's a little bit more cumbersome to write.
So maybe I've already had a lot of questions, so stop here. So
Thank you. And sorry for.